Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Hi, I'm Andrew Mellinger. I'm a software architect for the Software Engineering Institute's Emerging Technology Center. And today I'm going to talk with Ritvik Gupta, who is a software machine learning research scientist at the ETC, along with me. And we're going to talk about the use of artificial intelligence in humanitarian assistance and disaster response projects, which we currently refer to as HATER. Hi, Ritvik.
How's it going, Andrew?
Good. Can you tell me about kind of how you got to the SEI, how you got to the ETC, and what you actually do there?
Yeah, so I got to the SEI. So I graduated from the University of Pittsburgh, shout out Pitt, in 2017 with my degree in computer science, my bachelor's. And I was kind of looking around my life in general about, like, should I go to grad school? Should I just go work full time? What should I do? Really wanted to come to CME for a PhD. That's when I talked to Andrew Moore, who was a dean at the time, and he told me, like, you're so young, like, go work for 2 years, come back, like, get some money, get some experience, money mainly, you know. And, like, you know, you'll have more scope in your life to go do stuff. So I agreed, and I said, all right, I'll put off the whole grad school thing, but I'd still like to work in a place where I can still do that academic work and still do some research. As it happens, by chance, the SEI found me while I was giving a talk at a high school about machine learning, and they were like, you should come work here. And I said, sure. So I ended up here, long story short. But the team that we work in is called the Emerging Technology Center. And what we focus on is applied AML in all sorts of domains, human-machine interaction, machine emotional intelligence, and then advanced computing. Those are the three pillars. And so my background has been traditionally artificial intelligence, ML, and health, whether that be with I used to work at this awesome department at Pitt called the Department of Biomedical Informatics. They used to do all sorts of really cool, like, cancer pathology, like whole genome sequencing, whole genome, like, causality modeling stuff. That was really fun. But then I've also worked on the, like, more like electronic health record side of things and just epidemiology a little bit, some whole slide imaging. So, like, my background's really how do we take this really cool statistical machine learning or these AI capabilities and actually have direct impact on human health or human lives. And so when I came here, you know, my goals were really open-ended. It was first of all was let's go to grad school, which if you're working at CMU, I feel like that's pretty easy. But the goal was, like, I want to build a body of work that lets me do that, lets me do more of how do we take AML and impact human lives. So while I've been at the SEI, I've led a small research effort focused on robotics and specifically how robots understand anomalous behavior, not only in their environments, but also as they interact with different humans in their surroundings. And so that's been a lot of fun. So we've done a lot of work with inverse reinforcement learning to understand anomalous robotic behavior. Separately, we've done a lot of work with remote sensing, EO, or electro-optical imagery or synthetic aperture radar imagery, and understanding, like, what are different parts of the world which are damaged or which are, you know, about to be flooded or whatever. And then some, like, auxiliary work in just, like, adversarial machine learning or some other cool stuff. So really merging all of those gives me, I think, a broad platform to talk about how we can take AML and directly use it to help human lives directly, whether that be directly through their health, like it's actually impacting the way they spread diseases or the way they understand neuronal sheet damage, for example, or more abstract, like how do we assist first responders and disaster people to better understand what parts of the world are damaged after a disaster so that they can better plan logistics and resources, which then goes on and impacts human lives. Right.
So you mentioned different modalities like you know, computer vision and synthetic aperture radar. So can you talk about the background a little bit before we get into actually the HATER part? So what is available, kind of what's the state of the art, state of practice in those areas right now?
Yeah, so I mean the world of HATER. So computer vision is a specific field of machine learning, right? Focused on how do we use computers to do vision tasks, like anything with imagery, and then like SAR and EO would be modalities within that domain. But speaking generally, HATER is a we call it HATER. I feel people call it Hatter HA/DR.
You're such a
I prefer hater just because like rolls of the tongue and people think I'm talking about hating things. I don't know. But hater in general is a very broad field, right? So it can encompass things like computer vision. Like how do we use computer vision to do damage planning or something like that? How do we use computer vision to do routing across obstructed roads? But by all means, like hater can also involve things like rescue robotics. Like how do we build robots that can crawl around the rubble and find people? It can involve things like how do we spread how can we stop the spread of misinformation on social media during and after a disaster, which is very common. How do we understand disaster forecasting? Like if there's floods, how do we forecast where the high water mark will be? How do we forecast what will be impacted? What critical infrastructure is impacted? So the field is very broad, like NLP, computer vision, robotics, game theory. Like it's the whole gamut of the AI world.
Right.
I specifically focus on computer vision just because that's been my background, but that doesn't mean that we're limited in what we can do. My interests are then combining that with robotics, so not only can we, make predictions about the world, but then we can actually do something about them via robotics.
Right.
Either way, the goal is to make sure less human lives are at risk when we're responding to these things because they're really dangerous.
Right. So we talked before about some other projects you've worked on, like the Defense Innovation Unit's XView, that kind of led up to this. Can you talk about that a little bit?
Yeah, so there's this team of people in the DoD, and they're called the Defense Innovation Unit. They're based out of SF, and there's a small team in the Pentagon, I believe, in Boston, San Francisco, and Mountain View. And what their goal is to basically take some really, really cool commercial technologies that are available from startups or wherever in the world right now and translate them over to the DoD space to be highly applicable and impactful. So one thing that DIU focused on last year, back when they were so-called DIU experimental, because they weren't sure if that unit was going to do a great job, and they are, was they said that this whole world of operationalizing computer vision stuff that we do with satellites is really important. Like, it's not sufficient to just create prototypes and say, yeah, we can detect buildings or something. Let's get that in the hand of someone, who can actually do something about it, like who needs that information. So last year, DIU launched this thing called the XV1 competition. They created one of the largest overhead satellite imagery data sets where they had millions of buildings and just millions of objects overall that were very fine grained. So they had everything from like pickup truck to a pickup truck with a trailer. Except like these objects could be really small in the image. So like it could be like identify this as a pickup truck versus pickup truck with a trailer, and the thing is like 5 pixels wide, and it could be really dense. Like there could be over 1,000 objects in one small image, and so it could be really, really dense detection. The issue with XP1 was that like they weren't able to do the whole operational part of it. Like it's a really cool research data set. It's really hard. Like we competed in that and we got 5th place in the world. And in my opinion, our metrics weren't anything great. Like it was okay. Like we got like a mean average precision of like 0.28 or whatever, which again, on comparable data sets that aren't this difficult, the same model that we use could get a mean average precision of like 0.8. So like just for a comparison of the gap, like there's a lot of work to be done in this area. So it's a really good academic research data set, but it wasn't clear how to like make that useful for anyone doing operational work at the moment. So the goal was, DIU then reached out to us and said, hey, you guys did really well on this challenge. Would you want to help us figure out what we want to do for the next one? That's a little bit more operational. That's a little bit more impactful, but still involves computer vision in some way.
Right.
So we went through a whole bunch of ideas. We talked with USGS. We talked with FEMA, NASA. We talked with all these people who have all this data and all these amazing problems that I got to realize for the first time that like these are problems real people have to solve every day so that we don't get completely screwed when the next hurricane hits or whatever.
Right.
And so we ended up deciding on creating a challenge that lets people understand or lets models detect how damaged a building is after a disaster. So what happens is, I use California example because they do a pretty good job of it. After, let's say, a wildfire in California, they have about 24 to 48 hours to make a presidential declaration of emergency, and that lets them National Guard be militarized. It lets them do all these things that like enhance their response to these fires, and so what they have to do is they have to go in and give the declaration like we have 17,351 damaged buildings or whatever, and so we need help. that's a really exact count, and the way they do that is they literally send people in after disaster within 24 to 48 hours, and someone has to sit there and like count buildings.
So this is manual.
It's manual, and you can imagine how dangerous. Like if let's say it was a flood and there's down power lines in the water, and there's I don't know, alligators roaming the streets, or like looters, I don't know, shooting places up. Like you don't know, right? And so it's really dangerous to send people in after disaster to go and do this task just to declare emergency so you can get more help.
Right.
So the idea was like this happens everywhere. This happens in California, North Dakota. It happens around the world, in Nepal, everywhere. Like you need to be able to figure out what's damaged, how damaged is it, so we can not only do declaration of emergency, but we can also then respond accordingly, right? Like if I don't know this village is damaged in this remote part of Nepal, how am I going to get help or logistics or resources there? I'm not.
Right.
So what we've gone about and done is we've collected now this via our partners at Digital Globe, which is now Maxar. They have this amazing repository of satellite imagery from before and after disasters.
Mm-hmm.
We've gone in, we've collected that data, we've annotated it with not only where those buildings are, so polygons over buildings, but also we worked with partners at CAL FIRE, the California Air National Guard, FEMA, NASA, to create this scale that lets people assess on a scale of 0 to 3 how damaged the building is. Is it not destroyed, minor damage, major damage, or destroyed? Because right now they were using binary. They were literally like, is it damaged or is it not? And that's really great. Like that's really binary and doesn't really give as much context as you would like to have when responding to these things. So we're going to create the scale. We got the whole data set annotated, and we're going to be releasing a prize challenge coming up in the next week or so. That takes us past the data set. It's over 30,000 square kilometers of satellite image, annotated satellite imagery. That the challenge is create machine learning models that can find buildings and then tell me how damaged they are from electro-optical satellite imagery in the visible spectrum. So that's really exciting. That's called the XView2 challenge. If you go to xview2.org, you can find out more about it. But the prize pool is $150,000, so it's a massive prize challenge as far as machine learning challenges go. And the idea is that we'll get fully Dockerized containers back from competitors and whoever wants to submit a model, and the idea is that we'll then help transition those models over to the Cal Air National Guard or UN or NASA, or who can actually directly use this technology to actually do their work. So we're pretty excited for it. It should be a huge force multiplier for damage response, disaster response.
Right. So are you doing any AI yourself for this, or we're just supporting the?
We are. So not only are we creating the data set, we're also creating baseline models. We'll call them reference models, so that people can get started with the challenge. Not a lot of people have experience with working with like satellite imagery or like change detection and stuff like that, or just advanced machine learning methods. So we're creating a library of code that lets you do localization and classification or ordinal regression is what we're going towards over this data set, and then we're going to release it to the public when the challenge comes out so they can start working on top of that and hopefully beat us and do better. But yeah, and people don't have to use that if they don't want to. Like some people are very capable, and some people who are competing are part of major companies. So like they already have like well-established ways to do this, or invent new ways to do this task, which is what we want, right? If we were able to do it already, then we wouldn't launch the challenge.
Right.
Yeah.
Fantastic.
Yeah.
So then, what's your role after this then? So you're going to get the data back, and we adjudicate it, or how does that work?
Yeah, so I mean, we're working with the Defense Innovation Unit, who are working with some other partners and contractors to run the challenge. But our role is going to be basically to keep on continuing to deploy better baseline models so that people can keep continuing to work against a better and moving target. But in general, though, our role is to continue doing some good research. So find better ways to do this task and find other ways that we can be impactful in the hater space. So maybe we figure out that electro-optical imagery isn't the best or isn't the most useful for this task. Maybe we need to go over to synthetic aperture radar SAR imagery. So like we're going to be working on finding what's new and what's next, and just being ambassadors for bringing this world of AI and hater together. We've been trying, and we've been working with a group of some excellent faculty at CMU's campus and at Berkeley to create basically a center of excellence, a center of research for hater work. So Dr. Hyde Choset, Matt Travers at the CMU Robotics Institute have been working really hard over the past year or so to create like a center at CMU that lets faculty that focus on hater work come together and do all sorts of cool research together and publish under one arm. Equivalently, Trevor Darrell and his team at Berkeley AI Research Lab have been doing the same thing, and they've been working really hard to make sure that the work that they're doing, which they already apply to hater, is organized and under like a common umbrella. So we've been collaborating with them to see how we can make their work more impactful. We will be hosting at NeurIPS this year. NeurIPS is a very large machine learning conference in Vancouver this year. We'll be hosting the first ever AI plus hater workshop at NeurIPS December 13th. That is focused on bringing members from the AI world, whether that be robotics or computer vision or NLP or whatever, and people from the hater community, whether that be like people who do epidemiology research, all the way to people who do like from the Calvin Air National Guard, like people who do fire response or fire intelligence collection and go through intel cycle, together into one room so that we can understand the powers and limitations of AI, so that the hater people understand that, and then more importantly, I think for the scope of the venue, which is NeurIPS, so that AI people can understand what's lacking in their research or what's limiting their research to be perfectly operational, and get new ways to guide their research to things they may not have ever known about.
Right.
So we're trying to make that happen. We will make it happen on December 13th, and really we're hoping that to be a good event. We'll also announce the winner of the XV2 challenge at the workshop as well.
So along with a lot of the image recognition things in a very abstract way, can you give me some examples really quick about like what is actually discover out of using these techniques? I mean, so imagine a disaster. Besides saying, I've got a damaged building, what else is kind of on the horizon for things we could do? Things like, can I actually find people in the rubble or something else, or what's available? Yeah,
so again, like I think that's a very good example of finding people in the rubble, because that comes out of CMU, so it's close to us. So Howie Chosett and Matt Travers, they have this thing called the Biorobotics Lab. In the Robotics Institute at CMU, and one of the things that they make is called the Snake Bot. People have probably seen videos of it. It's this like literally this robot made of multiple independent components that chain together, and it moves like a snake, and you can control it like a snake. It rolls and it twists. And back when the Mexico City earthquake happened, like 2 years ago now, I think. Howie's team was actually called in to go to Mexico City and use a robot to dig through rubble and be able to assist in finding people and stuff. I don't know if they actually found anyone, but the idea was I think it was not one of the first times, but it was a really cool time where there was a real earthquake and a real big disaster, and people recognized the use of robots for getting in these really tight places that humans would never have a chance of getting into and exploring, and basically serving as a force multiplier for, can we find people when there aren't enough people on the ground to do that task? And I think it was a really cool demo of a technology that's only going to get more pervasive in the future. Like we saw with the recent Fukushima disaster, when the radiation's terrible, we send in robots so humans don't get completely destroyed. So they did the same thing with Chernobyl. So those are extreme situations. But even just giant things like, how can we use autonomous drones to locate stranded, isolated communities and drop them resources, or communicate with them? How do we I mentioned this, prevent the spread of disinformation. So a few years ago, I forgot which hurricane it was. It was one hurricane flooded the streets, and there was this picture circulating on Twitter of a shark swimming through the streets, and people were literally freaking out, like, oh, there's sharks in our street. And so what other people are doing is, can we use natural language processing and social media and whatever to find disinformation like this and help disaster agencies or coordinating agencies put a stop to it before it gets to like panic state. People aren't leaving their houses because the shark might get me or something, right? But again, there's so many uses, and the issue is that a lot of the hater world is so manual, because not only is the work to recover from a disaster completely manual, and so people don't really look beyond that, but the technologies to even evaluate those things are manual. So we were recently invited down to FEMA last week, to talk to their remote sensing people about what can we do with remote sensing to make disasters. And one of the things that I found out about, I didn't know this was a thing, was, I knew it was a thing, right? There's debris after disasters, but I don't really think about it. It just goes away, right? I've never actually understood, I've never looked into what happens. Someone has to get rid of that. And so there's contractors hired by the state, city, whatever, that take care of debris for them. But like how much debris there is, where that debris is like something that people just have to go find. So like understanding how big debris piles are is a problem that exists in the world, and like something I was completely unaware of. So Argonne, Argonne National Labs is actually building this whole thing with drones, which can do volumetric LiDAR scans of debris piles and give you an accurate, I don't call it an estimate, like an accurate measurement of like you have 35 cubic tons of debris in this area, and this is how much effort it'll take to move it, and this is how much you should be billed for that to happen.
All right. Well, thanks for coming by. We could talk about this all day, I'm sure. I think afterwards they'll have links in the transcription, other resources available, and they can follow us online. Thanks for coming.
And if I may add too, if you're interested in more resources about Hader and how Hader is being applied to AI, we have, it's currently being used for the workshop, but we have a URL called Hadr.ai. If you go to Hadr.ai, you'll be able to find some really cool resources that talk about how to apply Hadr to AI and what's possible and kind of the people working in this area. So it's a pretty good resource if anyone's interested.
Hopefully we can talk about XV2 after the challenge is done, right?
Absolutely. Yeah. Thank you.
Thanks.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.